Swayam Prabha. Digital India. Educated India.
So, in the last lecture, we were talking about surface plasmon polariton, what it means that, when you have a surface plasmon resonance. So, in the end, I was a little bit rushed up. So, if you have any questions, please let me know. Okay. So, the question was, we said that there is this plasmon dispersion and then there is this line, right? This is SPP, I said. This is the light line, LL, and this is my SPP dispersion. And I said when epsilon, this is a dispersion, right, that we got, that we derived. So, okay, this was dielectric and metal. That's the notation we used. So, we said when epsilon metal plus epsilon dielectric is equal to 0, we have a resonance where my kx becomes very, very large. The question was, what does it mean that kx is very large? Well, to understand that, we'll have to look at what happens. What is the meaning of kx and ky? So, they are the components of the wave vector. And we also know from our understanding of plane waves that kx square plus k, in this case if I confine to only xz plane, kz square equal to k naught square. We said the total of these two components should be less than or equal to k naught for a wave to propagate. Now, if I have kx to be much, much larger than k naught, then of course kz becomes imaginary, and because of that it is evanescent. So, if you have a very large kx, you cannot have such a wave propagating in the free space, and that is why we say that, okay, light line is this, and always waves can have to exist below this light line. The light, this is where the propagating waves can exist. Anything to the right is evanescent wave. But within the sphere of this evanescent waves, we have a special type of wave which can propagate at the interface, which has kx to be larger. What does it mean that kx is larger? Well, I can think of a wavelength. When I have a propagation constant k naught for a free space wavelength, for a free space wave, what is the wavelength? Lambda naught is going to be 2 pi by k naught. That is my wavelength. That's how I define the propagation constant. Now, if my kx is, let's say, in this case, I can define similarly for a surface plasmon polariton, I can define a wavelength, and that is going to be 2 pi by kx in my notation. Okay. So, I can even rewrite this in terms of 2 pi by k naught into k naught by kx. So, whenever you have a wave propagating at the interface, the ratio of kx and k naught matters. Okay. So, for example, if I take my incoming frequency to be this one, okay. So, omega by omega plasma frequency, I will take it to be 0.4. That is the frequency I chose. What is the difference between kx and k naught? K naught is a light line. So, this is my k naught, right? And kx is this red line. So, there is a small difference in that. Whereas, if I take another frequency, let's say of this one, omega by omega p is equal to 0.6. Okay. Now, clearly you see that at this frequency, my k naught is going to be this particular number, roughly 0.5. Whereas, my kx is roughly 1. Okay. So, if I take my omega incident equal to omega p by 0.6, that's the wave frequency I chose. In that particular case, my kx by k naught is going to be roughly 1 divided by 0.5, that is about 2. Okay. So, now what does it mean for that particular plasmonic wave, surface plasmon polariton? The wavelength of the plasmon polariton is going to be how much? Lambda SPP for this case is lambda SPP is going to be lambda naught divided by 2, right? Kx by k naught is going here, so 1 over that. So, lambda. So, the wavelength of the plasmon polariton is half the free space wavelength. But if I hit a condition wherein my omega d, so if I have a omega SPP, what is omega SPP? We saw that it is omega p divided by root 2. When does it occur? It occurs when epsilon dielectric plus epsilon metal equal to 0. So, I end up in a situation for optical constants where the denominator goes to 0. Essentially, kx is very, very large. In principle, infinite if I have an ideal wave. But of course, it's not going to happen. It's going to be finite. We'll come to that. But let's say you have, in this particular case, let's imagine for this frequency, let's say that this is my kx. Kx equal to, let's say 3. And my k naught is roughly going to be 0.6, let's say. Okay. So for this case, my kx by k naught is going to be 5. So at the plasmon polariton frequency, my lambda SPP, the wavelength of the surface wave, is going to be lambda naught by 5. So essentially, as I'm approaching the resonance frequency, I'm seeing that my wave is having much smaller wavelength than the free space. Okay. So this is the confinement we talk about, or how much smaller is the wave compared to the free space wavelength. Okay. Of course, this is also physically confined. These are all plasmon polaritons, right? They're occurring at the interface between, let's say, okay, I'm running out of space here. So, but let's say this is metal and this is dielectric. At the interface, these waves occur. So in the vertical direction, in the z direction, they're going to decay very, very fast. Okay. How fast? We will come to that. Okay. But we know that already, right? Kz. You know how much is kz? You can immediately calculate that's the attenuation constant. So 1 over kz will be roughly the distance over which the waves will decay. All right. Does that answer the question? Okay. Well, yeah. Nice. Thank you. Okay. There are a couple of things we actually did not discuss in the last lecture. Okay. Let me try to do that. Let me copy this and let me paste this. Okay. So basically I repeated it. Okay. So now let me clear up this. Okay. Yeah. So now what we said was omega d and omega metal, epsilon d, epsilon metal and epsilon d. Okay. So I have this situation. So we understand what this wave means, when this dispersion is there. And we started considering certain limits. Okay. First of all, at first case, epsilon d plus epsilon metal equal to 0, we saw what it is, omega equal to omega SPP. This is the plasmon, omega SPP equal to omega p by root 2. The plasmon resonance and very strong confinement of electric field, of the wave. Okay. Now let's take another situation, second one, wherein I'll take a omega much, much smaller than omega p. What do you think will happen? Any guesses? Well, to analyze this, we'll have to know what is the metal, right? So epsilon metal is simply, for an ideal Rood model, it is omega p square by omega square. If my omega is much smaller than plasma frequency, then my epsilon is going to be very, very strongly negative. Okay. Epsilon metal is much, much smaller than 0. When epsilon metal is very, very small, what happens to kx? Kx approximately will be k naught times. So metal is going to dominate. So effectively cancels out. So basically root over epsilon d. Right? So that is why you see that as we go to lower frequencies, the plasmon dispersion is coming close to the light line. Okay. That's what happens when you go to lower frequencies. What happens to the higher frequencies? So third case, what happens when omega is much, much greater than omega p? Well, what happens to epsilon metal in that case? Epsilon metal equal to, ideally it should be omega p by omega p square by omega square. Okay. So what will happen in this case? Epsilon metal tends to, as frequency goes to very high infinity, epsilon metal tends to 1. Okay. Of course, in reality for real metals, it's going to be some epsilon infinity, which is 3, 4, some number. But okay, for now, for ideal metal, epsilon metal equal to 1. It's going to be not negative. At frequencies much higher than the plasma frequency, it is going to be a positive number. It's like a dielectric. Even metal behaves like a dielectric at ultraviolet frequencies, right? So all of this, the conventional things that we talk about, they're all dependent on the situations. Depends on where you're talking. All right. So when you have such a scenario, what will happen to the kx? Kx equal to epsilon metal is 1. So roughly, let's assume that dielectric also is 1. So in this case, k naught into 1 and 1 divided by 2 root. So basically k naught by root 2. Okay. This is where the kx is going to be. So now, if I go higher than the plasma frequency, very high, I am seeing that the propagation constant is actually smaller than k naught. Okay, this implies lambda SPP is actually greater than lambda naught. That only then the kx can be smaller than k naught. Okay, so that's why this occurs to the left of the light line. So when you go to higher frequencies, you will see that this is going to be like this. Okay. And at the plasmon omega SPP, there is going to be a discontinuity that effectively is going to be like this. And because of the finite loss, okay, that's what is shown in the bottom here, figure here. So what you see is you have this light plasmon dispersion at higher wavelengths. It's actually coming down like this. At the frequency of SPP, resonant frequency, you have this variation. And any guesses? If I actually try to shine light at all these wavelengths across the plasma frequency, what will be the line shape that I get? So you understand what I'm saying? So I have somehow I'm able to couple. Of course, coupling to the surface plasmon polariton is actually a different job. We'll talk about it later. But let's say I'm somehow able to excite surface plasmon polaritons at different frequencies, right from 0.2 omega p to actually 1 omega p. Let's say I'm able to do that. What will be the line shape? What happens when a resonance is excited? Well, energy is going to get transferred into that and it's going to propagate. Rest of it is going to get reflected. Let's say I have a mechanism by which I have this interface of metal and dielectric on the top, and I have some light which is incident this way and it gets reflected, okay, normally. But then as I approach plasma frequency, some of it is going to get not reflected, but it's going to propagate as surface plasmon polariton on the interface, right? So the reflection should reduce. So if I look at the shape, what should be the line shape as I change the frequency? It's a narrow thing. Okay, narrow or not, we'll talk about it. The frequency, it should be Lorentzian. That's all you need. There is one model that you need to know. It's going to be Lorentzian line shape. And that is why you see in the frequency axis, if you turn your head by 90 degrees and see, essentially just like how the refractive index changes, that's how it's changing. It's reaching a peak, coming down, going to the opposite direction, coming back up. Isn't it? I can even think of multiple plasmon propagation, SPPs. I can think of, this is at interface between air and metal. I can even think of a SPP at the interface between metal and dielectric. Right? I mean, I can put a a strip of gold. I can think of a structure like this. In the bottom I have glass, 1.5 index. Then I have a strip of metal. Then I have air. Then I can think of SPPs at both this. Let's say in principle, if you are able to excite, they can actually propagate. Okay. Now, if I think of this medium, so you have this SPP propagating on one interface. Let's call it interface 1. And second interface is SPP propagating at interface, omega, basically in the metal and dielectric interface, the bottom interface. There are these two interfaces. So, let's say interface 1, I mean air and metal interface, there is a SPP. We already know omega SPP equal to omega p by, in this case it is omega p by root 2, right? For the air for the metal and glass interface, what will be the omega SPP frequency? Omega p by 1 minus omega p square by omega square is going to be minus 2 now, right? Just take it as epsilon as 2, okay? 2 plus 1, so 3. So now omega SPP is going to be equal to omega p by root 3, okay? Root 3. So that has a lower frequency, isn't it? That means red shifting.
Basically, N effective we need to check.
No, I mean, the substrate, right? Of course, there are some more issues here because there are these two SPPs which can actually interact and form hybridization, all that stuff. It can become complicated. But the idea is that if I think of this, as ideally there is no interaction between them, I can think of, in this particular problem, I can think of my omega SPP of the second interface, glass metal interface, to be omega p by root 3. So it's having a lower frequency, it's red shifted. Always it happens. Any resonance, optical resonances you take, one rule of thumb is, if you have a surrounding medium to be higher refractive index, it gets red shifted resonances. Okay. Same thing happens with LSPR. Change the medium from, let's say, air to water, you will see red shift. It gets red shift. Okay. So we will have some of these things in the problems. Let's please take care. Okay. We can also think of how much smaller is the wavelength of the SPP compared to the free space. In the direction of propagation, let's say, I have the wavelength, right? I can think of the wavelength as the length scale. Now, if I have my SPP to be wavelength to be large or equal to lambda naught, there is no confinement. It's like free space. But the moment I'm putting this interface, my lambda SPP is going to be smaller than the lambda naught. How much smaller is what I'm talking about. So kx by k naught, is it 5, is it 10, is it 100? If it's 100, then my SPP wavelength is like that much smaller. Okay. And of course, we should also remember, once the kx increases, automatically kz has to reduce. The other interesting aspect is, this is the resonance. Okay. What is the velocity of the wave at resonance? Well, if you look at any of this resonant, I told you when I talked about dispersion, in passing I mentioned, the group velocity is going to be d omega by dk. Okay. So essentially the slope of the dispersion tells me what is the velocity. If you have the light line, omega equal to ck, you take d omega by dk, you get c. The speed of light is c in that. If you take another medium like glass, it will going to be slightly shifted to the right. The slope reduces, the speed reduces. Now, when I go to my SPP and I see that my dispersion is practically flat, what does it mean? The wave is essentially stationary. It looks like a stationary wave. There is this charge oscillations that occur at the interface, but the propagation velocity is zero effectively there. The group velocity is zero. Okay. And at slightly lower frequencies, of course, there is some velocity. D omega by dk wave is propagating at that some speed. Okay. Well, it also ties into what happens, okay, so far we have talked about the dispersion relation. So let's say kx equal to k naught root of epsilon metal, epsilon dielectric divided by epsilon metal plus epsilon dielectric. All right. So we just took the epsilon metal to be 1 minus omega p square by omega square. But that need not be the true case all the time. You will have some imaginary part, right? Epsilon metal can be imaginary, right? Epsilon metal not can be, is imaginary, because there is a loss associated. So what does loss mean? Well, your kx is now, it's not going to be a simple number. It's going to have a kx prime plus ikx double prime. Okay, this is going to be real and imaginary parts to your propagation constant, kspp, right? And from the imaginary part, I can calculate how much is the propagation length. So propagation length is going to be 1 over kx double prime. So once I know my imaginary part, if I have a very large imaginary part, then the propagation length is going to be less. Right? So based on that, I can compute from the dispersion, I can compute my propagation length. And this is done, in this, you can actually go back and look at this reference. Essentially, you have the root metal and then you have the silver, which is a realistic metal. And you see that the propagation constant reduces as you go to higher frequency. Okay. And the take home message is that the propagation constant for SPP is about, in this case, let's say I assume a visible wavelength. Okay. This is going to be my lower energy. So 700 nanometers, the gray part, edges 300 to 700 nanometers. This is the visible domain. At the center of the visible domain, typically you have 200 nanometers, 200 micrometers. Propagation constant is going to be 200, roughly 200 to 100 to 200 micrometers and so on. So you might say this is a very small number, right? But you should also imagine what happens when you have a chip, right? On chip, the distances are never too large. I mean, we need to communicate information faster, but not over long distances. So this is still a prospective technology that can be used. But of course, the loss plays an important role, and there are a lot of effort in trying to minimize the loss. All right. So this is a big issue. So the wave on the interface is going to decay as it propagates. That's the message I just want to leave you with. Okay. And the wavelength of the wave is going to be smaller than the free space. Okay. Now, so that essentially brings me back to the point where I started this discussion on surface plasmon polaritons. So you have this charge density oscillations on the interface, and they can actually propagate. And you see here that this is scale over which the intensity is reducing as it propagates in this waveguide. The intensity reduces. And these are an analog of optical fibers on the chip. But they are much more lossy than optical fiber. Optical fiber can communicate information or transmit information over tens of thousands of kilometers, But if you have a plasmonic waveguide, well, so far it is very small. It's only for on the chip purposes. The benefit is that it is very, very small in size. It can be very small in size. The drawback is that it can't propagate information over long distances. So basically, this is one of the technologies that's been proposed as a possibility for on-chip interconnects. Because if you have regular dielectric systems, like an optical fiber, I can make it very small. If I make an optical fiber very small, the loss starts increasing. Okay, that's why we have the core diameter to be about 10 microns and the cladding to be 125 microns. That's a typical standard single mode fiber. If I go to 100 nanometer fiber, well, if I make it, my wave is not going to be confined to that. It's going to leak out into the structure, and that's why it cannot travel very long distances. But it turns out that if you have this plasmonic interconnects and things like that, you can actually beat that. So the idea is that the traditional CMOS technology is operating at these frequencies of up to gigahertz. So you have this technology going on like this, and in future slowly, we expect that there are these fundamental limitations to CMOS technology, wherein you can't increase the speed beyond a point; it saturates. On the other hand, photonics is the technology which really goes into much higher frequencies. So plasmonics is one of the potential technologies wherein you can combine these two for on-chip communications. Okay, that is why there's a lot of interest in plasmonics. One of the interesting directions. And so, yeah, this is a famous picture that I have taken from slides of Mark Progressma and Shalive. So what they are saying is, in this perspective article in 2010, what they're saying is, essentially you have the electronics which is all everywhere, microelectronics, where the devices are much smaller than micron, even up to the 10 nanometer scale. The frequencies are limited up to a few gigahertz. And the photonics is much larger in dimension, but it can operate at higher frequencies. Now, the possibility of combining the best of these two worlds, that is, have the frequency of operation of photonics, but the size scale of the electronic devices. The best of these two worlds is what plasmonics may provide. There are serious problems. We still are looking at how to solve those problems. So this is still an active research area, I would say. We don't know, but it's one of the ways which I think, one of the interesting directions which helps us understand various aspects of solid state physics. So that's why it's very beautiful. All right. So with that, I'll stop this discussion. And in the next lecture, I'll just talk about a few techniques to excite the surface plasmon polaritons. And then with that, I'll stop. All right. Thank you so much for your attention. Take care. Bye.